Good evening, ladies and gentlemen. Welcome to the Geological Society of London and to this, the 10th and final Society London lecture in 2014, entitled Terra Infirma, What Has Salt Tectonics Ever Done for Us? My name is Malcolm Brown, and I'm chairman of the Petroleum Group at the Geological Society. It's my pleasure to introduce today's speaker, Chris Jackson of Imperial College. Salt is everywhere, on dining tables, in food, and in health warnings on food. But it's not just for fish and chips or de-icing roads. Salt is a unique and underappreciated rock type. Salt has long been at the centre of mankind's development as a key ingredient in food preservation. And in the ground, it may sit still like any good rock should, or it may take it into its head to start flowing like a fluid. Salt's ability to flow leads to some of the most complex and beautiful geological structures observed on Earth. From an applied perspective, salt is one of the most economically important rock types, because in addition to its intrinsic value, it also forms seals to supergiant hydrocarbon accumulations in every corner of the globe. And in Brazil, we are very grateful for it. Chris Jackson, our speaker today, studied geology at Manchester University, where he stayed on for a PhD, completed in 2002, on the tectonostratigraphic development of the Suez Rift. He then worked at Norsk Hydro's research centre in Bergen, in Norway, until 2004. Leaving Norsk Hydro to pursue an academic career at Imperial College, Chris has continued to enjoy combining field and subsurface data, investigating soft sediment remobilization, the development of intrusive and extrusive igneous provinces, and the development of mass transport complexes. God, you do all that, do you? Amazing. Very badly. Ladies and gentlemen, please welcome Dr. Chris Jackson.
Right, thank you very much. Right, to get us started, we have to do a bit of work with you, or you don't get off scot-free. We have a poll here. Obviously, my role in this talk is to try and convince you that salt is indeed the best rock type on Earth, and because I'm a scientist, we need to be quantitative. Because of that, we need a vote. If you have a tablet or a phone, please go to govote.at, govote, all one word, .at. If you go there, you'll be able to type in this code, 592927. So govote.at, 592927. This has been tweeted already, and already we've got some responses in, and we indeed did this for the lecture this afternoon. Somebody's ringing in there. Okay, so what I obviously need to do during this talk is obviously try and shift some people who are kind of voting for granite. Why on earth would they do that? To salt, okay? So take some time. And while you're doing that, I just want to pull something rather mysterious out of my bucket at the front here. Right, for those of you watching on the camera who can only see here, this is a piece of silicon. This is SGM36. This is the material we use for salt tectonic modelling, and it indeed is Terra Infirma. It's basically like a solid, but as you will see if I plonk it here during the lecture, it will morph into something far more sinister, okay? So those of you down the front will be able to see this, and those of you later on at the end will be able to come down and have a look. So let's leave the vote running in the background there. So as you'll see, oops, I've not set it. As you'll see, as you go to the vote, there's a number of options for you. Sandstone, limestone, mudstone. I have good friends. Okay, so have a go at that. The lecture title is called What Has Salt Tectonics Ever Done for Us? But in the course of putting together this kind of talk, I actually decided to actually broaden it from what are my scientific interests, which is the salt tectonics. Oh, somebody wants to become really friendly with me. Who's got an iPad? Don't go looking in my browser history. So I wanted to broaden it, indeed. I wanted to strike off the tectonics. We will talk about salt tectonics. But we'll look more generally at salt's importance in terms of mankind's development. We'll also look at salt's importance and the mischievous things it can get up to. This talk will involve music. It will involve movies. It will involve intrigue. There'll be a bit of disaster. And, of course, it'll all be topped off with a heavy dose of salt to make it taste nice. For today, salt will be the star. To start off, I'd like to thank a few people who helped me put this talk together, Mike Hudek, Martin Jackson, and Tim Dooley, who've talked to me about salt tectonics for a number of years now, so from a scientific point of view. Robin Thomas as well, who unfortunately is not here, but has actually scored a piece of music specifically for this talk. So you're going to hear some music which is inspired by salt tectonics during the talk. Tanya Chong helped me get some rock samples which are available for viewing in the lower library. So we've got some evaporite rocks out there for you to get your hands on. And Kevin D'Souza provided me with this rather mysterious piece of material down here, which is already doing some quite weird stuff. They are all getting in the mood for Christmas, so happy Christmas, everyone. Most of us will think of salt as far as this image will show. So this is a salt shaker. So we see it on our tables every day and in restaurants everywhere we go, whether you're working class or middle class and you have a grinder, it's pretty much the same thing. What we do is we stick it on our fish and chips, or we stick it on every bit of food. And if we do that, then obviously we end up driving down the road and seeing this sign from the British Heart Foundation warning us about salt and our intake of salt. Now, you get this grinning idiot, depending on your political affiliation, telling you that salt is indeed bad for you, okay? So we have this love-hate relationship with salt from a personal point of view. We love it because it makes things taste nice. It also preserves things, and we'll come back to that. But equally, it can be dangerous. Over the weekend, we had our first cold snap. I went out on Friday night and had a rather lonely and fraught walk home at about 4:30 in the morning on the Saturday morning. And I was very lucky not to fall over because the roads were very icy because they hadn't started gritting yet. And obviously salt is very important for keeping our infrastructure moving smoothly in the UK and all around the world. You're probably asking yourself, so what else do I need to know? I can stick it on my food, not too much of it. I can want it on my road so I can drive. You may also be thinking, well, in terms of that vote, well, I've got sandstone. I've got the beautiful buildings in Petra in Jordan. They're visually beautiful. They have a lot of historical significance. Salt can't rival that. We may also want to think about carbonates. So these are limestones. This is the Portland stone. This is the building stone that my building where I work in the Royal School of Mines is made from, and a large amount of buildings across London and across the UK are made from Portland stone. Even shale and mudstone, fracking, shale gas. Oof. Okay. Even that which has been talked about in the London lecture series, you may be thinking, well, actually, even if I don't think it's a very beautiful rock, I actually think it's very useful and obviously has a really important role to play in energy for the whole globe. Granite as well. That very firm, rigid rock makes a good building stone. This is a photograph of the Aberdeen County House in the centre of Aberdeen on a very, very rare day of sunshine in Aberdeen. What I need to do, though, today is actually convince you, as shown in this image, that salt is beautiful. Look at that cubic form, sodium chloride, beautifully cubic, and you'll be able to see rock samples outside. So I'm going to convince you of its beauty. Unfortunately, you're not going to get all this for free. You're going to have to learn something. I'm going to have to tell you a bit about its physical properties. I'm going to have to tell you a bit about why it's so unique and why those properties allow it to do what it does. So I need to get rid of this sort of image and get you all fired up. I'll also tell you that indeed salt almost makes the world. Okay, so salt has played and continues to play a very important role in mankind's development and the way we trade and the way we actually feed ourselves as well. To get us started, I need to tell you a bit about how salt is deposited. Now, salt, what I kind of find quite unique about it is it's actually hidden in water. Okay, so it's in water, in seawater, and then it sort of appears, right? It precipitates, and then you put it back in water and it dissolves, and then you move the water over here, and then it appears again. Not many other rock types do that. So, and actually trying to communicate that's very difficult. So I decided to do it through the medium of a movie. Okay, this movie is by some kind of American who's got obviously a lot of time on his hands, as you'll realise. But he does actually, over the course of about a minute and a bit, actually show us a little bit about how halite and salts are precipitated from seawater. Okay, so we're going to run that through now.
Okay, everybody, today we are going to talk about precipitation. Okay, now I don't mean precipitation like rain or snow or sleet falling from the sky. I'm talking about precipitation of a mineral when it's in water and it's going to form rocks. So here we are in my kitchen, and we're going to start with
So that's seawater. He got his brother to go to the Atlantic Ocean off Long Island and fetch it for him, if you watch the whole video.
Okay, everybody, we're back, and as you can see, the water is now boiling. We're at, can you see that? We're at 19 minutes, so we're 19 minutes in, what's happening is the dissolved minerals, now that water that's left is saturated with the mineral halite. So what's happening is the halite is going from being dissolved in the water to being a solid. All right, everybody. Well, finally, we're now 124 minutes in, so over 2 hours, and all the water has evaporated. And what is left is, I don't know if you can see that, it is white. It is a mineral, and that mineral is halite.
So thank you, Mr. America. Obviously, when we're making evaporite rocks in nature, we don't boil it, but we evaporate that water and we precipitate out that halite material. Now, what you notice in that video is he put in a lot of water and he got out relatively little salt. So obviously, seawater can yield a finite amount of salt depending on the concentration of the minerals within that water. So we have this idea of a seawater yield. So let's take a kilometre deep, a kilometre deep body of water and evaporate it. That only yields 16 meters of salt, so a relatively small amount of salt. Of that, the lion's share is halite, so that's the stuff you put on your chips and on your roads. Carbonates and gypsum in here precipitate out earliest because they're the least soluble. They precipitate out earlier. And bitten salts, these potash salts, to precipitate out late. And that's telling us about the precipitation sequence from seawater. There's a problem here, okay? We have very, very thick salt sequences in nature. Therefore, we need to keep replenishing the seawater, don't we, to actually build up those thick, kilometre thicknesses of salt deposits. So we need to have a mechanism for doing that. And it's useful in some ways to think of that in terms of the salt budget. Before I get onto that, this thing started to go crazy. So now I'm going to do a little bit of magic. I'm going to put a cup on it, a £2 coin, a £1 coin, and a 5p. And we're going to leave that through the rest of the talk and see what happens to it, okay? So we have the salt budget. We have the ocean off to the right. We have a lagoon or some kind of enclosed basin in the centre here. We can add seawater to that by actually seeping it through this barrier, having runoff from the barrier of marine waters. We can also have surface runoff in addition to hydrothermal input as well. So we can have hot fluids bearing salt coming up to the Earth's surface and evaporating out and depositing salt. We can also have the competition enforced upon it by rain. We're actually making things less brine-like, less saline by actually raining on it as well. So we have this competition. That's what gives rise to this salt budget. So if we can keep flooding or fluxing and then evaporating, flooding, fluxing, evaporating, we eventually can build up great thicknesses of salt rock. So we have water level rise in the basin, the salt stays in solution, like the guy when he first poured it in the pan. And if sea level falls or the water level falls, we get salt precipitation. That occurs in two different areas. This is the kind of slide I showed before. So this is in an area quite near the ocean, which is separated from a depot centre or a basin in here by a sill, which is 100 metres or so high and a few kilometres wide. And we get fluxing through that to allow us to deposit these salts in these saltern halites or these saline mud flats. Okay, so this can be at or around sea level. So these are marginal marine. We also have giant intercontinental basins. These sit below the ocean level. So this is sea level in here. So these are things like Death Valley, okay? And this is where we get a large amount of saline input from groundwater because we're actually too far away from the ocean to really flux through the continents through here. But we actually have a large amount of material coming in or salt-bearing fluids coming in from the continents and also in hydrothermally as well. But again, this allows us to develop very thick sequences if we have ways of replenishing that. The world's largest salt flat is in southwest Bolivia, the Salar de Uyuni. Salar obviously means salt, which is down here in southwest Bolivia and is so large it's visible pretty much from space. It's 100 kilometers for scale in here. This is north. This white area is the salt flat in here. Does anybody know what these black dots are, these black things? Near the Andes? Volcanoes. So there's volcanoes active around here, which in the recent past have actually erupted and magma has been transported over parts of the salt flat and actually split it into two. Now, in terms of size, it's kind of hard to get your head around. That's 26,000 kilometers squared. Okay, the majority of fluids the majority of salt there is derived from hydrothermal systems. In terms of size, if we compare it to the UK, for those of you who know me, I will never hesitate to actually talk about my hometown and county. So it's about the distance from London to Derby, if you would have it, from north to south. So that's how big it is. You know, it's a kind of big area. Now, I'll come back to this later on in the talk, but that is a baby compared to some of the ancient salt deposits we have in the geological record. And I'll come back to that later. Just a bit of eye candy from the example from the Salar. In here, you can see here's the salt flat in here with all these gypsums and halites precipitating out, and this big volcano in here. Truly lunar-esque landscapes. This is halite, which is being caused by fluids seeping above the water table and precipitating out halite at the Earth's surface. The amazing thing here is that the aggradation rate, that is the rate of deposition of the salt, is 1 to 2 centimeters a year. It's actually building up, okay, which is way beyond the depositional rates typical of a lot of other sedimentary environments. What I find even more amazing is the way they found that out. It's by radar. They actually scan the Earth and they can actually detect changes of centimeter scale of the Earth's relief and actually work out how quickly this is degrading. Obviously, there's times when the climate is wetter and it's dissolving, but overall, the maximum rate is 1 to 2 centimeters a year. Most of you are familiar with the Dead Sea. The Dead Sea, some of you may have even been there, floated on your back like in your nice holiday pictures. That's located here off from the Levant margin in the eastern Mediterranean. This is part of a system which is deposited within a strike-slip plate tectonic environment. That's where the plates are sliding past each other, hence this very strong north trend to the basin. Stunning images from the margins of the Dead Sea. You can see the evaporites precipitating out all along the margin, and this is a truly stunning image. These are carnallite crystals. These are those potash salts developing these beautiful frondose flower-like patterns, which are the really, really saline end of things. Martin Jackson, who provided me with this image, said that the water there had the viscosity of engine oil for a car. It's that soupy and it's that saturated, hence you can float on it pretty much irrespective of your size. I've told you a bit about salt and how we get it and where it's deposited, and now I want to kind of make the case for how important it has been in the past and how important it continues to be, using a number of examples. The first example comes from China, and particularly from east central China, in Lake Yucheng. It's the home to one of China's earliest prehistoric salt works. The record of salt mining or salt harvesting going on there goes back about 8,000 years, or 6,000 years. There's a written record from about 1,000 years ago. Every summer, the lake kind of obviously dries out when it's warm in there, and you get precipitation of evaporites around the margin, and people come along and harvest that. Because of that, it's obviously been the source of much conflict, as I'll say during the talk at numerous occasions. Salt is a huge commodity, and it was important very long ago in the past and continues to be now. So there's a lot of conflict about the ownership of the lake, the rights to harvest from here. Because it was one of the times when you could use clay pots, actually take the water, transport it, and then evaporate it off somewhere else. It was actually one of the first examples of where we actually took a commodity, moved it, and then used it somewhere else. So quite a stunning history. Not as stunning as this guy. He is a Taoist monk, an alchemist. I was rubbish at chemistry at school, but these guys weren't. Weirdly enough, these monks were actually living around the lake and using the fluids to try and get the elixir of life. Okay, so they were adding this and mixing it with different things. What they unfortunately came up with was this. Does anybody know what this is? Sodium nitrate. Does anybody know what sodium nitrate is used for? Boom. So it's one of the important, it's an older ingredient, or it's a kind of ingredient in gunpowder. Okay, so what these monks did is they actually developed something which actually was used in gunpowder, and weirdly enough, they were looking for the elixir of life, and what they found instead was one of the devices which has been responsible for killing more people on Earth pretty much than any other man-made device, right? So they kind of didn't really hit the mark particularly well. We also can think about when we move the salt somewhere else, what we can use it for there. We can obviously use that salt to preserve things. Salt, when you add it, it actually takes in the moisture or water being one of the key things that the bugs and nasties want to use to actually live and degrade the meat and the food we eat. We can preserve fish and vegetables. You could even, if you're into it, preserve human beings, or if you're really weird, cats and pets, mummified animals. It's very important though, isn't it? Because we can actually take salt and actually preserve things and move it from A to B and actually stop it from rotting so we can actually feed people in far-flung places. Obviously in the long past that's important before we had these middle-class fridges and freezers, like this fancy Smeg one here. The people who understood that more than most were these guys, the Egyptians. And obviously the mummification process, which was kind of most famous because of its use in the Great Pharaoh era, but actually has a history dating way before that, they were using salt deposits to actually preserve human beings. One of the most famous being Tutankhamun. Now, you know, when I'm putting together this talk, I find out lots of interesting facts, some of which make it in here, some of which don't. But it's interesting because when you think about it, the Egyptians actually sent large amounts of food with their pharaohs on their journey to the afterlife because they thought the afterlife was a long way away, which I guess it is. It's possibly even further away than Derby is from London, right? So they actually sent, in those tombs and in those temples, they sent along food. Now, in the case of Tutankhamun, they took a large amount of food and packaged it all up and mummified it along using the salt that they had to hand in some of these saline salt pans in the middle of Egypt. Now, I want to read it off from here, what they sent with Tutankhamun, what they actually preserved in salt. He had 116 baskets of fruit, 40 jars of wine, loaves and cakes, jars of honey, almonds, spices, bowls of peas, onions, lentils, garlic, several joints of roast beef, and a duck. It doesn't say whether the duck was dead or alive before they put it in and salted it, but I'm hoping it was already done. But just to make the point that even in ancient history, you know, there's that the same value we have of beef jerky and things we eat now, which is salted. We kind of take them for granted, but back then it was actually almost part of the spiritual underpinning of many societies. Salt was. So I haven't got time to go into the religious side of it in this talk, but it's amazing when you do a bit of research. Does anybody know where this is? The US of A. Now, you would think the US of A, being like about 3 weeks old, might actually not have a long and interesting history with salt, but actually it does, you know. It's not just those ancient civilizations, which are thousands of years old. In the US, they also have had their recent history impacted by salt, most notably during the Civil War. In the Civil War, the battle between the Confederacy states in the south and Union states in the north was held in through this battleground through these kind of, well, neutral states, if you will. Now, one thing the officers, the army did when they couldn't afford to feed the soldiers or couldn't afford to pay them, they gave them salt as payment. Now, the reason they gave them salt as payment is because those people, if they caught food, the soldiers, they could preserve the food. There's an old adage, isn't there, that if you keep an army fed, it stays strong, and if it stays strong, it can win conflicts, okay? And they understood the importance of that actually by keeping people fed, it kept them strong and allowed them to fight, even if they had no money, okay? So obviously very, very important to the soldiers. In fact, the word salary, which we obviously see maybe once a month, maybe, on a slip. The word salary, sal, comes from salt. It's a form of payment using salt rather than in terms of money. Now, in the Civil War, one big conflict that was fought in the town of Saltville, no guess as to why it was called Saltville, aside to say there was a big salt work there. And obviously, look where it's positioned, at a very strategic location in the northern part of the Confederacy states. So it was continually raided by the Union states during the Civil War. In 1864, in October, there was a raid by the Union down into Saltville, and they tried to take over the salt works. It was repelled by the Confederacy in Virginia there. In 1865, in the December, they eventually came back and burnt it to the ground, thus cutting off salt supply to the front line in the eastern Confederacy states, therefore allowing the Union to encroach southwards through into New Jersey. So salt was very central to that. It was the whole end game. If you could basically cut off that salt supply, you could actually stop feeding soldiers. I don't know many other rocks which perhaps hold so much sway in military conflict as salt being one of them. In fact, the phrase salting the earth comes from the idea that armies went in, they ransacked an area, and then to stop things growing, they threw salt all over the ground to stop anything ever growing there again. So even if they didn't kill everybody, for those harsh winters and the periods afterwards, the population couldn't actually grow any food. So salting the earth, again, is another military phrase. Okay, we're saturated in salt. For those of you down the front, you may see some rather crazy things going on. My cup has keeled over. This thing is spreading into a big amorphous mass. My pound coin, actually my £2 coin is deeper down than my 5p, which is about the same as my pound coin. Have a think about why that might be, why they're sinking differently into our salt analog. We need a break. And for that break, I'm going to bring you a commercial break, brought to you by Salt. Now, what I'm going to show you through here, I'm going to make the case set to the music by Robin of the beauty of salt. I'm going to show you a series of images that are going to go by. This music was written by Robin, and it's to actually, you'll hear at the beginning of the piece and the end of the piece, the salt shaker. You'll hear the music build and build and build, and that's to show the deposition of the salt layers and the building as it gets to its apex is when we get the big diapirs, or these big domes forming, before everything settles down again towards the end of the piece. I'm basically bringing rock and roll to the Joel sock. So I hope you enjoy it. Now, I would be lying if I was to say that salt was always beautiful. It is capable of some horrible, horrible things, and that's where I'm taking you all now. Even though I am a self-professed halophile, I will actually acknowledge the fact that there has been some bad behaviour by salt, and in fact I will show you what I think is the poster boy of bad behaviour by salt, which is the case of Lake Peigneur in Louisiana in the 1980s. Lake Peigneur is situated a couple of 100 kilometres to the west-northwest of the Mississippi Delta in here in Louisiana, north of the Gulf of Mexico. Lake Peigneur looks fairly innocent, a circular lake, a couple of kilometres wide, a canal draining to the south. That will become important in the story I'm about to tell you, with a bunch of rednecks living around the edge. If those who've been to Louisiana, it's a slightly scary place at times. The Jefferson Island salt mine is shown here in cross-section. I'll take a moment to walk you through this. This, for scale, is about 500 metres along here. Here's Lake Peigneur. The top of the Jefferson Island salt diapier in here, this salt dome, had been mined since the 1920s for salt, so there'd been a load of mine shafts drilled into here. Texaco came along, 21st of November 1980, and what they were planning to do was to drill for oil in the rocks next to the Jefferson Island salt dome. So not in it, but next to it. However, due to an engineering error, it's great when you read about it on the internet, somebody dropped a 0 in some division. They did this instead. They drilled directly into one of the shafts, therefore opening up a direct connection between the lake and that open network of shafts, which were about half a kilometre below the Earth's surface. Okay, so you can imagine what happened. What happened was the rig obviously fell over because the rig was seated on the lake is normally about 10 metres deep, so the whole thing toppled. Everybody jumped off, started swimming for the shore, no problem, just big catfish in the water, there's nothing to worry about. The fresh water obviously headed straight down a drill bit. The drill bit was 14 inches in diameter. But obviously, as it started to spin and this vortex opened up, it started to carve a much bigger hole. So all the water went down. but due to very good escape plans that were in place and some heroic actions by some of the miners, all 55 miners who were down half a kilometre below the ground got out in time. Okay, so they all made it. This whirlpool carved out this hole on the lake bed and also carved out a much bigger hole and made the lake bigger. What's also the problem if you send a load of fresh water down into a salt mine? You can work it out. You make the surface area bigger by dissolving it, and therefore you can dissolve quicker and quicker and quicker. So suddenly you have a very big problem on your hands, and all hell breaks loose. The whirlpool was a hungry old boy. Okay, so as this whirlpool got really, really big, it started to consume things that were in the lake, not just the water. It gobbled up 2 drilling rigs. It gobbled up a tugboat. The tugboat wasn't even in the lake, it was in the canal to the south. It got sucked into the lake and then down into the plug hole. You think that's impressive? It took 11 barges, industrial-sized barges, went down into the plug hole, into the sinkhole. The lake drained of 13 million cubic meters in 3 hours. Now, how big is that? Those numbers mean nothing. It's 13 times the Albert Hall. Taking some inspiration from the Beatles, A Day in the Life. The lake refilled a few days later but with a 50-meter high waterfall. This is the highest waterfall there's ever been in Louisiana's history because it's as flat as a pancake. There are no waterfalls. And this one made one which was as big as Nelson's Column. The best thing was, though, 9 of the tugboats came back. When it refilled, they popped up, they bobbed around and were spat back out of this hole. So, you know, the insurance write-off was not quite as bad as you thought. So let's see, you know, because everybody wants to see a good disaster movie, right? You all want to see, like, the complete hellish stuff going on. So let's click here.
The whirlpool is basically a vortex of water and mud that is flowing down into a fairly confined space. And that whirlpool is basically flowing downwards under the force of gravity, pulling sediment and other materials down with it.
The whirlpool's sucking force pulled heavy-duty barges toward it as their crews leapt for safety. Men watched with jaws agape as 11 barges and a tugboat disappeared into the vortex. Those are 4 fully loaded flatbed trucks spinning helplessly in the whirlpool.
Look at this over here, look! Look at this!
Could things get worse?
Yes.
Yes. Delcom Canal, which normally flowed away from Lake Peigneur and into the Gulf of Mexico, actually reversed direction under the intense sucking power of the whirlpool. As the water rushed into the now nearly empty lakebed, it formed a 150-foot waterfall, the highest ever in Louisiana.
That's the only time the Gulf of Mexico flowed north.
As the water rushed into the mine, its rapid displacement of the underground caverns shot a deafening blast of compressed air, and later, a 400-foot geyser up from the mine shaft.
To see something like this, it was terrible, really. I thought it was the end of the world.
Now, the end of the world. I don't know about you, ladies and gentlemen, but if I'm around the end of the world, I want it to look a little bit more impressive than that, right? I mean, it was pretty impressive, but not quite the end of the world. This old timer here, look at his hat. I survived Lake Peigneur. He was fishing with his nephew for catfish. And there's a whole story. If you watch the video, it's like 12 minutes long, and there's bits about him like swimming around with his nephew holding catfish under each arm and stuff. It's very funny, but this old timer was very happy to get out. So, I mean, in this story, it's probably, I'm not sure if salt behaving badly is like fair enough, but men behaving badly, mathematicians, engineers behaving badly, somebody made a giant screw up, right, and drilled into that thing. But it's just to show you that salt, because of those properties, because it can dissolve, because we're mining it, and because we're trying to exploit it in many different ways in the subsurface, it is a danger. This is another interesting story about how salt can cause trouble and dissolve. This is from Spain, from the Cardona, Las Salinas, no problems with the name, what that means, where there they drilled also down into a mine gallery, hit a natural groundwater conduit, so a conduit which was already there. The water went down into the mine and carved out a 4-kilometre long set of meandering channels which cut through salt. This isn't the greatest image, but this is a map view looking down into the mine. This is the existing passage, but look what it cut out. This amazing meandering channel system. That was in 1998. There were another 2 floods in the subsequent 2 years which cut out this even bigger one. Just to show you how impressive that is. This is a cave down in the Les Salinas mines. This is Eocene salt in here. This is one of the tunnels that's been carved by this deluge of fresh water, which is obviously dissolving the salt. These are gravels from the river that went 50 meters down into the caves. So there's riverine gravels now down at 50 meters in these salt caves. Mining as well, so it's not just in the deep surface, also when we come up into the mining area, we're also concerned about anomalous zones. These are places where the salt, which is otherwise impermeable and has low porosity, we can have fractures, we can have pockets of brine, so salt water, oil and gas. We can have non-evaporite inclusions, so we can have sedimentary rocks and igneous rocks trapped in the salt. Obviously, if you're a miner, the last thing you want is something which isn't pure salt in your salt body. You do not want to be taking that and then trying to process out. It's worthless. More fundamentally than that is, so if you think of this example here, you don't want to be taking this oil-stained salt in here. You'd rather have the pure salt because you've got less processing to do. More fundamentally, when we're drilling in the deep subsurface, because of what the salt is doing down in here, as you'll be able to see later on, salt moves. Okay, we'll come on to that in a minute, but it moves. So if we're drilling boreholes through salt, one problem we often have is we often get the salt flowing in and constraining and breaking the borehole. So often we'll drill a hole, we'll case it, we'll put something around the edges of the borehole to keep it stable, but salt will keep pushing and pushing in and can eventually damage the borehole casing. So salt in that way can behave badly and create a challenge when we're drilling to deep depths in the subsurface. We can also get these pockets of brine. So this again is coming back up to the shallow subsurface. So in the Zechstein salts in northeast England, in the Bulby mines in here, there's been 300,000 meters cubed of brine in 1 year actually flowed out of a pocket of brine within a salt body. That causes a huge problem, not only to life, but also to clean that up afterwards. Certainly in this case, because it was associated with an oil slick. So this is a meter for scale. So an oil slick in here, which you basically don't want deep underground for obvious reasons. So salt can behave badly, and this is another example. This is from 1945. This is German fighter jets which were being constructed and stored within an abandoned salt mine. This was discovered by the US Army in 1945 as they were advancing. I put this up not because I think it's salt behaving badly, but merely because I think it's mankind not really showering itself in glory and salt being actually kind of used in a less than admirable way. Now comes some numbers. We need to talk about the physical properties of salt, because to give you the context of how salt is good for us, I've talked to you about how it's evil. I'm going to need to talk to you about how it's good, but I need to tell you a bit about how it deforms and some of its properties before I do that. Salt is weak. Okay, as you can see here, this salt analog we have here is obviously deforming under its own weight. It's not a hot table. We're not boiling it. We're not doing anything. It's weak. To make that point as a graph, everybody likes a graph after work, don't they? Do you? Probably not. This is depth here, 0 to 10 kilometers. This is rock strength from 0 to minus 50. So this is in tension. So this is if we take a rock and do this, how strong it is. On the right-hand side of the graph is the rock strength in compression. Okay. All you need to take care of on this graph is that all these black lines show that the rock is getting stronger with depth. So the shales and the sandstones and the limestones. The only rock that doesn't is salt. It basically, if anything, stays the same or gets actually slightly weaker with depth. So all the other rocks around salt are strong and the salt is really weak. So you can obviously start to see why that ductility allows it to flow like a fluid. Think of it another way. This is the Earth's surface with a cat on the top of it, the supersalt, the salt, and the subsalt. So we have rocks around it. To show that graphically, here's the strength, and this is depth. These rocks in here are getting strong with depth, but then we have this unit of weak salt in here, and then we have some strong rocks down in here. Imagine having a Victoria sponge with too much jam in it. Okay, think of it like that, which would be great, wouldn't it? If all Victoria sponges were only jam. So we have this layer of gooiness in the middle, and we have these strong brittle rocks around it, okay? So you can imagine now what might happen. So let's think about what happens if we break these strong rocks above it. What then becomes important is density. Because if the salt is less dense than the rocks above, the salt may rise up if we break the rocks above the salt. Indeed it is. Depth, 0 to 7, it should be kilometers, 7,000 meters in here, and density across the top. Shales, which are shown in blue, and sandstones in brown, become denser with depth. That's because we're swashing them. We're compacting those rocks. They become their sediments at the surface, and we swash them to make them rock. Salt has the same density all the way down. So you can see there's this critical point, which is the majority of the Earth's subsurface, where salt is less dense than the rocks that surround it. So we have something which is weak, we have something which is less dense, and we have something which has properties that allow it to flow like a fluid. To make that case, or to make that kind of point graphically, I'm going to show you this movie here. This clear layer in the movie is going to be silicon, so it's the material I have on the table here, and this is our salt analog. This is sand above, this is imitating our brittle rocks overlying the salt. And what we're going to do is we're going to stretch or extend that overburden and see how this layer deforms through time as we extend this layer above here. So density and strength are going to play a role in this model. For scale, this is centimeters, so this is 5 centimeters, so this model is about this wide. And the model in here is going to run for about 7 hours, okay. So it's quite a slow model, but it's speeded up because you haven't got 7 hours, I guess. So you can see the stretching of the overburden occurring in here, and you can see what the salt is doing. It's flowing up into the space, into the chasm, into the void created by the thinning overburden, and it's rising up and up because this is pressing down on here, on the layer in here. This is pressing down on the layer in here. This area is thin, so through buoyancy, it can rise up through that weak, thin overburden. That's exactly what's happening here at the table at the front. I do encourage you to come down and have a look. The cup has already gone all the way through it, and we've actually got a bulge away from that down on the front here. So when we think about these salt diapirs, and we're trying to get an idea of their dimensions and sizes, because I've not really talked about how big these structures are going to get, okay, because that is one of the most impressive things. We use seismic reflection data. So Rebecca's here in the audience. I thank you for the image. So what we do is we set off a big boom bang, we can stamp, we can use drop an elephant, we can use dynamite, we can use all sorts of things. We set off a shot in here, the sound waves, the sound energy goes down into the Earth's subsurface, bounces off a bed, comes back up to these things we call receivers, and we listen for that sound, and from that we can work out what the subsurface structure of the Earth is. Okay, so that's called reflection seismology. We get images which are quite stunning like this back from this. So this is from about 3 kilometers below the Earth. The layered material in here are sedimentary rocks. They're just sands and shales laid down in a kind of fairly well-behaved manner. This transparent blob in here is the salt. The reason the salt is very transparent when we look in seismic reflection data is because it's very, very strained. It's flowed like a fluid, therefore we've had massive deformation of the crystals, of the grains, of the beds, of all the units in there. Unlike these rocks, which are slightly deformed and folded, but are nowhere near as deformed as the units within this thing we're calling a diapir. Okay, so this is a salt dome some of you may have heard of. No scales on there, deliberately. Here's another example, underburden in here. We have these large salt diapirs above in here, so you can see this transparent. This is the top of the salt, going down somewhere through here and up here within this other salt diapir. Remember, the original salt layer would have been just tabular, but because we're loading it differently like we're doing down here on the front table, because we're loading it, it's flowed up into these large diapir structures. That's the horizontal scale. People often go, when they see horizontal scales in seismic sections. This is a kilometre. These are about 10 kilometres apart, these diapirs. This is from here to Wembley Stadium. Okay, so there's this basin in between. What is more impressive, I think, is the height of these things. For scale, I've put in here Ben Nevis at the scale against this diapir. This diapir is about 2 kilometres high. Ben Nevis is 1.3K. So we're talking about giant mountains of salt beneath the Earth's surface, okay, which have actually swollen up and flowed up and formed these large diapiric structures. This is all in 2 dimensions. When we look in 3D, we see a range of different structures going from salt rollers and salt welts and salt anticlides, these small low-relief domes or these low-relief buckles, all the way through to these giant diapiric walls, which are several kilometres tall and several kilometres wide. As we come along this axis in here, we start to see some real exotica. We get these kind of weird wing-shaped diapirs. We even get diapirs which are completely friendless. They actually are floating surrounded by the country rocks, so the rocks which originally were above them. So it's actually detached off and is floating like a fluid within the overburden. To make that point more graphically, I show you an image here from the Danish North Sea, Danish Central Garden. This is the seabed here. These are these giant salt diapirs in here, so this is 3-dimensional, so you should be able to work out the depth perspective quite straightforwardly again. The scale is 1 kilometre. The amazing thing here is the scale is 2 kilometres. These diapirs are about 4K high, half the height of Everest. And these formed over the period of about, in this case, about 40 million years, okay, in the Earth's history. So they're very slow-moving beasts, like our, much slower than our fluid, our analogue in here, because we haven't got that long to wait around for our model results to come back. But you do get these very dramatic structures. This image here, again, is not a particularly nice image. It's pretty low resolution. This salt wall in here is quite long. The only reason I show this image is because, bizarrely enough, I found it on a creationist website, which I'm not sure if I'm allowed to show in the Geological. But it was on a creationist website, and they're even showing salt diapirs as well. So here you see these diapirs, and here, this diapiric chain in here, this salt wall is about 30 to 40 kilometers long. Okay, so again, the scale is very important. So we've gone all the way from these small grain scale things, depositing little bits of salt, to forming layers which are allowed to deform into things which are half the height of Everest. Salt is not just restricted to its movement in the subsurface. Indeed, in this model I showed you, right at the end, it actually got up to the Earth's surface and was breaking through. As you can see here from our salt analogue, once it gets there, it has not finished. It has still got some fun left in it. This is a cross-section, kind of a schematic cross-section through a salt glacier. As you can see in this diagram here, the salt is, so this is kind of an image in here, this is punctured up through the overburden rock in here. We've got this feeder pipe. We have this central dome, and then these beautiful salt glaciers, which are actually kind of flowing down away. These are some Google Earth images showing this. This example in here is about 5K wide. This one is about 10K, this wide valley in here. These are not volcanoes. These are salt glaciers. These domes you can see in here, this is in the Zagros in Iran, and here are the central domes, and we can see these beautiful salt glaciers spreading away from here. What's impressive here is the rate at which they move. Locally, the rates of salt flow, bearing in mind this is a rock, okay? This flows in a solid state. It's a rock. It's not a fluid. It flows at meters per year, which is kind of human hair growth rates. Well, my hair, less so. But, it flows very quickly, and people can actually measure that by putting GPSs on salt glaciers and seeing how quickly they move around. So salt can do a lot of great things in the subsurface and do a lot of great things even when it reaches the surface. Finally, I'm going to tell you now, based on all those information about the physical properties of salt, why salt is interesting and why it's good for us in terms of some of the good things it's done in terms of the petroleum industry. To give us some context here, I kind of show the scale of some modern-day salt basins. This is the Salar de Uyuni here, which is one we looked at earlier, Great Salt Lake, Dead Sea, the Danakil, some of you are familiar with these places. This is 100K for scale. If we put at the same scale some of the ancient salt basins, and now these are the ones which are trapping hydrocarbons, this is at the same scale. This in here is the Zechstein. This is a Permian 240 million year old basin in here. We have the Luan salt, which is Jurassic, 160, 170 million years down in here. We have in here the Hormuz. We have these giant salt basins. To give the Zechstein some context about how big that is, because that's one that's actually sort of almost beneath our feet here. This is the Zechstein outline in grey against a map of Europe. We are here. This is Norfolk and through here, so here's the UK coastline. It's a truly pan-European salt basin, 200 and something million years old, okay? So a giant extent. To make that point about the size of it, we can fit all of those modern salt basins in it and spread them out still a little bit, and they take up nowhere near as much as those ancient salt basins. So in the past, we had some truly amazing size salt basins, which if you think about the climate, the amount of water, the depressions on the Earth's surface we needed, because one thing in here I've not really talked about is we need the Earth to be subsiding to preserve all this, okay? Kilometers of salt. The Zechstein had an original thickness of probably about 1.5 kilometers. Salt's great, low porosity, low permeability, but obviously if we want to appeal to it as a key component of petroleum systems, we need it to be geographically widespread. This map here is of the globe. Ignore the colours. As you can see just from the colours that we have salt basins over large parts of the Earth. There's the Zechstein. This is the Messinian salt when the Mediterranean dried out in the late Miocene in here, where I did my PhD in the Gulf of Suez into the Red Sea in here. You can see salt deposits there. There's the Luan salt. These are all the salt deposits which are trapping the kind of reef recent giant hydrocarbon discoveries offshore Brazil and offshore West Africa as well. So you see we have them in a lot of places. What I quite like is this map, not because it's graphically nice, but because it actually shows something quite interesting about how salt basins are related to some of the giant fields. Now by giant, we're talking about fields which are over 500 million barrels of oil. Gulf of Mexico, big salt basin. Large parts of the Middle East, lots of salt in there. Up in the North Sea, Danish sector, the Norwegian sector, large salt basins in there. West Africa, modern discoveries or more recent discoveries off here in Brazil. We have a nice overlap between salt basins and these giant fields. Why is that? Because salt is impermeable, largely, and because it has very low porosity. So what we want when we kind of trying to create a hydrocarbon trap and preserve hydrocarbons are these three basic elements, four elements. One is a source rock, that's something to generate hydrocarbons. So this is from Kimmeridge Bay, some of you may have been there on the south coast. So organic rich you can set fire to it. We want our reservoir rock to be porous. We want a porous sandstone, for example, in this layer in here, which has, as shown in this thin section, this blue resin here is showing the pore space, so lots of room like a sponge to soak up the hydrocarbons. And we also want a seal rock. Now we want the seal rock to be impermeable because we want it, as shown in this diagram in here, to seal in all the hydrocarbons in the reservoir rock below. This is a thin section through a deformed piece of halite. You can see it's crystalline. You can see it has incredibly low permeability and incredibly low porosity. So it actually retains the hydrocarbons because the buoyancy forces in the fluids are pushing and the gases are pushing up, but it keeps it down and in there. Salt is ideal then if we look at this diagram because it's impermeable. If we have one of those domes, one of those diapirs pushing up through the Earth's subsurface as shown in here, we can obviously trap these black patches of hydrocarbons with a seal, we call it a side seal, against this hydrocarbon accumulation. And then like the Texaco guys were trying to do and made a big hash of it, you could drill down into here. The Texaco guys in the Lake Peigneur example went into there, that was the problem. But they were exploring for things which were on the sides in here. We can also get traps above due to deformation associated with the salt. If we think about some real examples, because this is nice and conceptual, we can think of the auger field in the Gulf of Mexico. This area in here, if I trace it out, this is the base of the salt. So you can see this area where we've got this really chaotic seismic signal is salt. The layered reflections out here, the nicely layered reflections of the rocks, the sedimentary rocks, the non-salt rocks outside. In here we have source rock, in here we have reservoir rock, in here we have seal rock on top ends, and here we have this really nice side seal of salt. So the hydrocarbons can come up here against the salt. In Augerfield, there's 250 million barrels of oil recoverable. In place, there's more, but we can only recover a certain amount of hydrocarbons often because of lots of different reasons. It doesn't come cheap, $1 billion development to get that out of the ground. This is a mere baby compared to some of the discoveries that have been made subsalt offshore Brazil. So much so, this was so famous, I remember being in a hotel in Luanda once and seeing it on the CNN news when Lula was actually discovered. In here we have the salt is in here, so top salt is this. You can see this nice diapir in here and all this intrasalt deformation. This is the base of the salt. The reservoir is in here, it's some carbonates. And the source rock is down in here. The source rocks expel hydrocarbons, come up into the reservoir and are trapped at the top of the seal in there. This is a monster, 5 billion barrels recoverable. Okay, that's recoverable. Think how much there is in addition to that. We've got 500,000 barrels of oil per day, they think, when they bring 300 production wells on stream. 300 production wells to produce. This is the whole cluster area now in Brazil. So these numbers change depending on who you speak to and how happy they are to tell you the real numbers. But you can see in here what they're going to do, or what they've done is drilled through this thick salt down into these subsalt reservoirs in here. So it's great. The other reason salt's important here is because even though these reservoirs are deep, and the reservoirs could be cooked and not very good, salt has very high thermal conductivity, so it can cool down your rocks underneath. Okay, so it can keep your source rock and reservoir cool. It's not going to come cheap. $100 billion. In fact, is that number right, Malcolm? Can you tell me BG's point on this? Don't answer that. It's a big number, says the man who knows a lot more about this than I do. It's going to cost a lot of money to produce this, and there's a load of challenges engineering-wise to actually get this all out of the ground. But what I'm trying to say here is salt has been central to the discovery of these kind of hydrocarbon provinces. Just a kind of rather complex slide from offshore, the offshore Gabon, showing again the salt in pink here, some big sort of traps developed due to folding of sandstones in here, lots of prospectivity in the subsalt in here. There's been a dry well drilled recently off in this part of the world. But salt is still going to be very important when we look forward to how petroleum systems are going to be exploited in the future. So luckily or unluckily, we are pretty much at the end. I believe there's a wine reception. I'd hate to keep you from it. We started off this talk by saying what you knew about salts, and that was probably the familiarity or the over-familiarity of what you see on your kitchen table, what you see in your restaurants, what you put on your fish and chips, and indeed the fact it may one day kill you. Also that we can grit the roads with it. So there's all these kind of common ideas we have about what salt is, and I would say it's all born out of a very domestic understanding. My hope during this talk is that I have convinced you that salt is beautiful all the way from the grain scale. Even those images I showed you through the animation, there's lots of things which are just visually very striking and lend themselves to very, very amazing images. I also showed kind of 3 examples or 3 case studies of how salt is important in terms of how it's made the world and how we've used salt as a species. And instead of those bored kids at the end, hopefully now you're a little bit more like these little happy chappies down in the bottom right here, that you've actually learned something but also found it interesting, and with you, you will take this in your hearts, salt, not too much, and that I've managed to convince you all to be halophiles. Now this is an organism that lives in high salt concentration, and the name comes from the Greek word for salt loving. So thank you very much.
Fantastic, fantastic. Right, we've got time for a few questions. Before we take them, if you could just wait for a microphone, because we're recording this, and I think you're already on the iPod, on the
podcast and some other things. Yeah.
You see, so we're going to sort of duplicate that.
I'll just go forward to this if any questions come in. We're gonna hold another vote. Right. Okay. So this is the end of the talk. So go vote.at. This is a different code. Type it in and vote again. I'm going to see if I can get some of those critical swing voters in the middle counties, as they say, and see how we go from there. But please, any questions?
Questions? Yeah, we'll just wait for the microphone.
Yes, my name is Alois Varjo, and I'm actually a botanist and not a geologist, but I've always been intrigued by the story, the geological story of the evaporation of the Mediterranean Sea.
Yeah.
And I understand that came about because the isthmus between Gibraltar and Tangier was closed.
Yeah.
And so the ocean could no longer come in. And there were apparently not enough rivers to fill the basin. Do you explain these enormous salt basins that you have found, or that have been found from geological past, in a similar way?
Yeah, it's a very good point. So for those of you who don't know, there's something called the Messinian salinity crisis, one of the most catastrophic events in Earth history. Catastrophic and amazing because it was so quick, a few tens of thousand years, really, 100,000 years. And what happened is the Straits of Gibraltar basically got blocked off, so the Atlantic was no longer supplying marine waters into the Mediterranean. So the Mediterranean basically dried out pretty much. So the Mediterranean lake floor was way beneath the Atlantic sea level. That's obviously a kind of Goldilocks scenario for actually then depositing a large amount of salt, because you've evaporated a load of water, you can keep replenishing it intermittently, but you've also got a big hole to put those salt rocks in. The Santos Basin salts are the salts which are in the South Atlantic, so the things I do research on. They have a very similar genesis in that they were formed as the Atlantic opened, but there was a volcanic ridge at the bottom which actually blocked off large parts of the South Atlantic north of the ridge, called the Florianopolis Ridge. Actually, north of there, you actually managed to evaporate off a lot of saline water. The Zechstein was the same as well. It had an opening northwards into the Boreal Ocean, so this was during the late Permian, but it was so narrow and restricted that the Zechstein salt basin could actually evaporate. So it was actually still marine connected, but the amount of marine water that could come in actually still wasn't enough to stop that area from drying out, and intermittently it was probably closed as well. So yes, in some ways you always need to get that soil restriction, but you can't be too restricted because you need a source of the salts to go into the basin. So if you can have some seepage reflux or hydrothermal activity or runoff of salt-bearing waters, that still helps.
Great, thanks. Other questions? Back.
I'm finding it difficult to understand how salt can flow. Does it maintain its crystal structure?
No, it flows as a solid state, so it's actually always a rock. So one thing when I started learning about salt, I actually assumed it was a fluid, so it melted. The melting point of halite is kind of 800 degrees, okay, so that we don't achieve that. So it's actually flowing as a rock. So the crystal structure becomes strained. So there are measurements being made of what the crystal structures in a salt rock which hasn't moved and those that have moved. And you actually see that the lattice is strained by up to 10%, so there's an asymmetry, so it goes from being a cubic mineral structure to being non-cubic, okay? So you actually strain it. Other rocks don't do that because basically they're so brittle that they actually just fracture before they ever really flow, unless you melt it, but that's something different, okay? And you can melt salt rocks as well, but then it would become a fluid, but then it would be a magma, or it'd be inclusions within a magma, which is a different thing entirely. So, I mean, one of the key things is we use this modelling material like this silicon in here, which has now completely swallowed up my coins. And that has a very fast strain rate, you know, it kind of moves very quickly. Natural salt obviously deforms much more slowly. In the subsurface, the time it gets very fast is when it gets to the Earth's surface, and then we lubricate it with water, and we actually get lots of very rapid deformation of the salt in those cases.
Thank you.
Okay. Time for one more question, I think.
Everybody senses, oh no.
Oh, at the back. Yeah. So just wait for the microphone.
I really want to know the difference between rock salt and sea salt concerning putting it on food.
The expensive stuff is the Malden, right? I mean, in all seriousness, the kind of most expensive, most desirable salt is the stuff which hasn't been treated. So salt which is harvested in the original way, so the salt marshes down in Essex, for example, where Malden comes from. That's the purest sea salt. The stuff we get in the cheap restaurants, which is where it's all iodinized and it's all been treated so it can be transported and doesn't actually absorb moisture, so it doesn't kind of clot together, that's the cheaper stuff. So in terms of rock salt and sea salt, yeah, I mean, there are compositional differences. I'm just trying to think how best to explain it. I guess sea salt is derived naturally from seawater, whereas rock salt could be derived from other origins, so not necessarily just from seawater, but also from hydrothermal or continental runoff as well.
You can find rock salt, you know, in the supermarkets, same as sea salt for putting on food, and that's what I was curious about, to know whether or not there's any sort of real difference in the composition. Is sea salt healthier than rock salt?
Which one is least bad for you? Okay?
I'm not Jeremy Hunt, thankfully. I mean, there may be an answer there.
Oh, yeah.
I used to work in the salt industry, so effectively, I guess in some ways it's the same because they both come from the sea originally. But the difference would be that when you take your cheap salt, you treat it and you remove some of the components. So some of the like magnesium salts and some calcium type carbonate salts and things like that. So it's not exactly the same once it's processed. Yeah. So I don't know which one's better, but I know that there would be a difference because some of the components aren't present in the other salt.
Yeah, I'm not sure which one would be better. I mean, in terms of whether it tastes better, that just depends on whether you believe that if something costs more, it tastes better, I guess.
Unless you've got a doctor in the house, you could tell
yes.
us. I don't know. Okay, I think it's 7:05. I think there's some drinks upstairs. So I'd just like everybody to thank Chris one more time. I thought it was a fantastic lecture. It was really good. Oh, all right.
So just a couple of things to close off. We're gonna kind of hopefully now look at the vote results. So we had, let's see if this works. So we had at the start, we actually had salt. Maybe I'd managed to kind of infiltrate the kind of Twitter sphere before my talk. But I had 12, 15, we had 56 responses, so 20-something% was salt. Oh dear, I don't want to press this button now to see what's happened here. Oh, there's been no vote. Oh, yay! There was some rather disparaging Twitter traffic earlier on, basically saying, why would anybody vote for Slate? Was what somebody said earlier on. Not my vote. So yeah, please come down and have a look at this silicon.